This screencast involves automated insulin dosing simulations. So we want to be able to address the following. Does meal announcement or feed-forward control impact the closed-loop performance? What is the effect of sensor noise and bias? And what are typical performance metrics used in closed-loop automated insulin delivery systems? This is a closed-loop block diagram that also includes a feed-forward component. We've presented this in a previous screencast. And so what we want to do in this particular screencast is conduct simulations for the meal carbohydrates being consumed. So we have 3 meals plus a snack with varying amounts of carbohydrates, 70 grams at breakfast, 50 grams at lunch, 75 at dinner, and 40 grams at an evening snack. We want to understand what the level of closed-loop performance we achieve if we include feed-forward control, which is also known as meal announcement, compared to not including that information. We also want to understand the effect of noise on the measured glucose signal that's being sent back to the controller, as well as bias and quantization effects. We're using a digital PIDY controller with parameter values from Cesar Palerm in a publication from 2011. So the corresponding proportional gain, interval time, and derivative time are shown on the right-hand side. We have a sample time of 5 minutes for this controller. In the closed-loop simulation studies, we're going to compare the PID performance with feed-forward and with feedback only. Compare CGM sensor and blood glucose because they can differ. First of all, there's a lag between blood glucose and the sensor reading, but also there may be bias and noise involved in the sensor reading. We're going to report the percent time and range for each variable and control strategy. In each simulation study, the top subplot is going to have the blood glucose as a continuous line and the continuous glucose monitor, the sensor, as a plus symbol. And the bottom subplot is going to be the insulin delivery rate. So in this particular simulation, we're looking at the PID controller with feed-forward, that is, with meal announcement, and that performance is shown in green. In the top plot, we have both the CGM and blood glucose. There's only a slight lag between the blood glucose and the CGM, and what we notice is the large bolus each time a meal is being consumed. So in terms of the performance metric, the blood glucose spends 4.2% of the time in hypoglycemia, a large percentage of the time, 86.3% of the time in the desired range of 70 to 180, and then 9.4% of the time in the slightly elevated range of 180 to 250 milligrams per deciliter. And the mean blood glucose level is 116.7. which is actually pretty phenomenal. So it's very rare for an individual to actually be able to achieve that level of performance. And then the CGM, because it lags the blood glucose, has slightly different metrics. Then what we've added here is the study shown in blue where we don't use the meal announcements. So there's not an insulin bolus given at mealtime. So then the integral action of the controller has to bring insulin up higher each time after the meal. And clearly the performance is not as good. You can see both the actual blood glucose as well as the sensor reading or spending a lot of time above the desired range of 70 to 180 milligrams per deciliter. And that's also reflected in this table where now we see that, well, we also have a substantial amount of time where it's spent at low blood glucose levels, 9.3% of the time, only 67.5% of the time in the 70 to 180, and then a substantial amount of time in the 180 to 250, as well as 250 to 350 milligrams per deciliter. So we have a substantial amount of hyperglycemia, but the mean blood glucose level in the end is not all that bad. But the trade-off has been that we've actually had this hypoglycemia late at night, which is definitely not desirable. So what we've shown is the meal announcement that was in the green curves with feed-forward control provides substantial improvement in the time and range that's desired, the 70 to 180 milligrams per deciliter compared to feedback only, and also reduces the time in hypoglycemia compared to feedback only. And in these simulations, there's no sensor bias. And I should note that the combination of feed-forward and feedback is often called hybrid closed loop in the diabetes literature. Now, quantization, noise, and bias. So CGM to the nearest 1 milligram per deciliter, random noise, the variance of 2 milligrams per deciliter through a first-order averaging filter, and then positive CGM bias. So in the next simulations, the CGM, the sensor reading, is going to be 10 milligrams per deciliter greater than the actual blood glucose. So in these studies, you can see on the top, for example, whether it's PID only without feed-forward control, the CGM is reading higher because of that positive bias. And that's also the case when you do have meal announcement shown in green. Again, the CGM is higher than the actual blood glucose. So what happens then is, because the CGM, the sensor signal, is biased in a positive fashion, the actual blood glucose, being 10 milligrams per deciliter lower than the CGM, puts us in an undesirable range with 22% of the time spent in hypoglycemia, that is the 50 to 70 milligrams per deciliter range. And then if we have just the PID feedback only without feed forward, again, it's not quite as bad, but because that sensor bias, we're spending 10.9% of the time in the undesirable hypoglycemic range. And we also end up being a little bit higher in the hyperglycemic range compared to feed forward and feedback control. So sensor bias of plus 10 milligrams per deciliter means the sensor reads higher than the actual blood glucose. But the problem is the controller only sees the sensor, so you don't really know what's happening with the blood glucose levels. So what's really happening is they may not realize it unless the individual then does a particular finger stick measurement. They're spending way too much time in hypoglycemia. So the next simulations, we're going to show a negative bias. That is, the sensor is reading 10 milligrams per deciliter lower than the actual blood glucose. And that's a little bit hard to see on this scale. But again, the CGM shown as the plus signs as reading slightly lower than the actual solid blood glucose for both the feed forward and feedback only. And what you're finding in this case with the feed forward and feedback is the blood glucose now is spending 4.2% time in hypo versus the CGM. But the only thing you really care about is the actual blood glucose. And in this particular case, the blood glucose is spending a substantial amount of time actually in the desirable range of 70 to 180 milligrams per deciliter. And the mean blood glucose is actually very good. And then finally, with the PID feedback only, what we're finding is we have a slightly lower percent of the time that we're spending in the desirable range compared to using a meal insulin bolus. So that's not surprising. And the actual mean glucose level then is substantially higher when you're not using that feed forward information. So in this particular case, the sensor has a negative bias that reads 10 milligrams per deciliter less than the actual blood glucose. So although the sensor spends time in hypoglycemia, the actual blood glucose has a pretty high time and range, particularly when we use the meal announcement feed forward combined with feedback. And our experience in clinical trials is that sensors do tend to be biased slightly low, probably to reduce this risk of hypoglycemia. Finally, I should note the new generation of continuous glucose monitors, glucose sensors, have good factory calibrations with little bias. So to summarize this presentation, meal announcement or feed forward control improves the closed loop performance. This is also called hybrid closed loop. Sensor noise and bias can decrease performance, and it's particularly dangerous when the CGM has a positive bias. The sensor could indicate safe control, but the actual blood glucose would be too low. The time and range, particularly 70 to 180 milligrams per deciliter, and mean blood glucose are important performance metrics.